Section: Introduction. In this section, we discuss the significant progress made in large language models, LLMs, and how they have transformed artificial intelligence research. These models can now understand, generate, and make nuanced decisions. Recently, we have seen the widespread use of reinforcement learning, RL, as a method to enhance LLMs after their initial training, leading to better alignment with human values, improved long-term reasoning, and adaptability to different environments. A key part of RL is reward modeling, which helps create accurate reward signals for LLM responses. Our findings indicate that when LLMs receive high-quality rewards during training or inference, they perform well in specific areas. However, these high-quality rewards often come from carefully designed environments or specific rules, making it harder to generate rewards in more general contexts where criteria can be complex and unclear. To improve LLM performance across a wider range of applications, we need generalist reward modeling. This requires flexibility to handle various input types and the ability to generate accurate rewards in different domains. Additionally, we need to enhance the scalability of reward models during inference, which involves producing better reward signals and learning scalable behaviors. We have identified several methods for reward generation, including scalar, semi-scalar, and generative approaches, each affecting the flexibility and scalability of reward models. For example, pairwise models only evaluate responses in relation to each other, while scalar models struggle to provide diverse rewards for the same response. Although various learning methods exist to enhance reward quality, few focus on scalability during inference, leading to limited improvements. Our research aims to address this gap by exploring different reward modeling approaches. We found that pointwise generative reward modeling can effectively handle single, paired, and multiple responses, thus overcoming some flexibility challenges. We also discovered principles that can guide reward generation, which may help improve the quality of rewards and enhance scalability. To achieve this, we propose a new learning method called self-principled critique tuning, SPCT. This method allows generative reward models to adaptively generate principles and critiques based on the input, leading to better rewards in general domains. We developed DeepSeek GRM27B, which is post-trained using SPCT and can scale inference by sampling multiple times. This approach allows for the generation of diverse principles and critiques, improving the accuracy and granularity of rewards. Additionally, we introduced a meta-reward model to further enhance scaling performance. Our empirical results show that SPCT significantly boosts the quality and scalability of generative reward models, outperforming existing methods and models in various benchmarks. We also found that DeepSeek GRM27B performs better in inference-time scaling compared to larger models, despite some challenges in efficiency in specific tasks. Overall, our main contribution is the introduction of SPCT to improve inference-time scalability for generalist reward modeling, resulting in the development of DeepSeek GRM models. We also present a meta-reward model to enhance performance beyond simple voting. Our findings demonstrate that SPCT leads to significant improvements in quality and scalability over existing methods and models. Section Summary. In this section, we discuss the advancements in large language models, LLMs, and the importance of reinforcement learning, RL, and reward modeling, for enhancing their performance in diverse domains. We introduce our novel approach, self-principled critique tuning, SPCT, which improves inference-time scalability and quality of GRMs, leading to the development of DeepSeek GRM models that outperform existing methods in various benchmarks. Section: Preliminaries. In this section, we compare different reward modeling, approaches, which are influenced by how rewards are generated and scored. We identify three main reward generation methods: scalar, semi-scalar, and generative. The scalar method assigns a single value to each query and response. The semi-scalar method provides both a textual critique and a scalar value. The generative method focuses solely on creating critiques, from which we can derive a reward value. For scoring patterns, we differentiate between pointwise and pairwise approaches. The pointwise method gives each response an individual score, while the pairwise method selects the best response from a set of candidates. To enhance computational efficiency during inference, we emphasize sampling-based methods that produce multiple reward sets for the same query and responses, which we then combine into a final reward. The scalability of RMs at inference time depends on the ability to obtain varied rewards through sampling. Scalar RMs often struggle here due to their consistent reward generation, while input flexibility is determined by whether the ERM can evaluate single, paired, or multiple responses. Pairwise RMs typically find it difficult to assess single responses and often need additional techniques for multiple responses. We also discuss how generalist RMs must generate high-quality rewards across diverse domains, where criteria can be complex and explicit references may not exist. To tackle this, we use guiding principles instead of rigid rules for reward generation. These principles, initially introduced in constitutional AI, help shape the data pipelines for large language models, LLMs. We conducted preliminary experiments to see how effective principles influence reward quality, using specific subsets from our benchmarks. We generated principles with GPT-4 and evaluated their effectiveness by comparing self-generated principles with filtered ones. Our findings indicate that while self-generated principles do not significantly enhance performance, filtered principles can greatly improve reward quality. Building on these results, we developed self-principled critique tuning, SPCT, a new method for pointwise GRMs that learns to create adaptive, high-quality principles to guide critique generation. SPCT involves two phases, an initial rejective fine-tuning phase and a rule-based online reinforcement learning phase, which enhances the generation of rewards and critiques. We also propose a shift in how we view principles, suggesting that they should be integrated into the reward generation process rather than treated as a separate step. This means that GRMs can generate principles based on the input query and responses, allowing for a more adaptive reward generation process. By generating principles at scale, we can improve the quality and detail of the rewards, which is essential for effective inference time scaling. Section Summary. In this section, we compare different reward modeling, ERM, approaches based on reward generation paradigms and scoring patterns, highlighting how these factors influence inference time scalability and input flexibility. We also introduce self-principled critique tuning, SPCT, to enhance reward quality by generating adaptive principles that guide the generation of critiques, ultimately improving the overall performance of generalist RMs. Section: Rule-based reinforcement learning. In this section, we propose SPCT to enhance the generation of principles and critiques in GRMs by combining rejective fine-tuning and rule-based reinforcement learning, RL. For the rejective fine-tuning, our main goal is to adjust the GRM to produce principles and critiques in the correct format for various types of input. Unlike earlier approaches that mixed different response formats, we utilize a pointwise GRM to generate rewards flexibly for any number of responses in the same format. In constructing our data, we not only use general instruction data but also sample trajectories from pre-trained GRMs based on queries and their responses from ERM data, varying the number of responses. We perform this sampling multiple times for each query. Our rejection strategy is straightforward. We discard trajectories with predicted rewards that do not match the ground truth or those where all trajectories are correct, making them too easy. We denote the ground truth reward for a response to a query as R_I, and we ensure that the predicted rewards are correct by confirming that there is only one maximum ground truth reward. However, we noticed that pre-trained GRMs often struggle to generate accurate rewards for some queries within a limited sampling quota. To address this, we introduce hinted sampling, where we add the maximum ground truth reward to the GRM prompt, hoping to improve alignment with the actual rewards. In hinted sampling, we sample each query and its responses once, rejecting only incorrect trajectories. We also found that hinted sampling can sometimes lead to shorter critiques, especially in reasoning tasks, highlighting the potential advantages of online RL for the GRM. Next, we fine-tune the GRM using rule-based online RL. We apply the original GRPO setup with rule-based outcome rewards. During this process, the GRM generates principles and critiques based on the input query and responses, and we compare the predicted rewards to the ground truth using accuracy rules. We do not use format rewards. Instead, we apply a larger penalty for KL divergence to maintain format integrity and reduce biases. The reward for each output encourages the GRM to identify the best responses through optimized principles and critiques, facilitating effective inference time scaling. To enhance the performance of DeepSeek GRM for generalist reward generation, we explore sampling-based strategies for better inference time scalability. We analyze previous methods and their limitations in the appendix. In our voting process for pointwise GRMs, we sum the rewards to determine the final reward for each response. This approach effectively expands the reward space, allowing the GRM to generate a wider range of principles, which improves the quality and granularity of the final rewards. More principles can better reflect the true distribution of judgments, enhancing scaling effectiveness. To ensure diversity and avoid positional biases, we shuffle responses before sampling. To address potential biases or low-quality outputs from the voting process, we train a meta-ERM to guide it. This meta-ERM is a pointwise scalar model that assesses the correctness of the principles and critiques generated by DeepSeek GRM using binary cross-entropy loss. Our dataset includes trajectories from non-hinted sampling in the rejective fine-tuning stage and those sampled from DeepSeek GRM. The guided voting process is straightforward. The meta-ERM provides meta-rewards for sampled rewards, and we select the final outcome based on the top meta-rewards, filtering out lower-quality samples. Section Summary. In this section, we propose SPCT, which combines rejective fine-tuning and rule-based reinforcement learning, RL, to enhance the generation of principles and critiques in GRMs. We utilize a pointwise GRM for flexible reward generation, implement hinted sampling to improve reward alignment, and employ a meta-reward model to guide the voting process, ensuring high-quality outputs while scaling inference effectively. Section: Experiment Settings. In this section, we evaluate the performance of various methods using different ERM benchmarks across multiple domains, including reward bench, PPE, RMB, and real mistake. We apply standard evaluation metrics for each benchmark. We measure accuracy in selecting the best response for reward bench, PPE, and RMB, while we use ROC-AUC for real mistake. To handle ties in predicted rewards, we shuffle the responses and identify the best one based on the highest predicted reward after shuffling. For our baseline methods, we re-implement several models, including LLM as a judge and others, using compatible training data and settings. Our methods include DeepSeek GRM27B and variations on different LLM sizes, such as DeepSeek V2 Lite and DeepSeek V3. We train the meta-ERM on Gemma 2 to 27B and report default results using greedy decoding with a temperature setting of 0.5. In our results, we compare DeepSeek GRM27B against public models and baseline methods. We find that DeepSeek GRM27B generally outperforms the baselines and competes well with strong public RMs. With inference-time scaling, it achieves even better results. We observe that scalar and semi-scalar RMs show biased performance across benchmarks, excelling in some areas while struggling in others. LLM as a judge follows a similar trend but performs lower, likely due to a lack of principled guidance. Overall, SPCT enhances the reward generation capabilities of GRMs with fewer biases compared to scalar and semi-scalar RMs. Regarding inference-time scalability, we see that DeepSeek GRM27B shows the most significant performance improvement with up to 8 samples and continues to perform well with larger inference compute. The meta-ERM effectively filters low-quality trajectories, and LLM as a judge benefits from using token probabilities for voting. However, Cloud Gemma 2-27b shows limited performance gains due to a lack of variance in scalar reward generation. In our ablation study, we find that even without initial rejective sampled critique data, general instruction-tuned GRMs improve significantly after online reinforcement learning. Non-hinted sampling appears more beneficial than hinted sampling, highlighting the importance of online training. We confirm that general instruction data is crucial for GRM performance and that principal generation is vital for both greedy decoding and inference time scaling. Finally, we explore the scaling of inference and training costs for DeepSeek GRM27b. We find that direct voting with 32 samples can match the performance of larger models, while meta-ERM guided voting achieves the best results with just 8 samples. Testing with a smaller dataset reveals that expanding reasoning tasks does not significantly enhance the performance of generalist RMs. Section Summary. In this section, we evaluate various methods on ERM benchmarks using standard metrics, finding that DeepSeek GRM27b outperforms baseline methods and achieves competitive results with public models, particularly benefiting from inference time scaling. Our ablation studies highlight the importance of online training and general instruction data for improving performance, while also demonstrating that the meta-ERM enhances scalability and robustness in decision-making processes. Section: Related Work. In this section, we discuss the advancements in generative reward models, GRMs, which mark a significant change from traditional scalar reward models, RMs, by representing rewards as textual feedback or scores. This allows for more complex reward representations and greater flexibility in evaluating both single and multiple responses. Previously, the LLM as a judge approach enabled either reference-based or reference-free pairwise judgments for assessing LLMs. Recent research has utilized offline reinforcement learning, such as DPO, to train GRMs, integrating tools and external knowledge, and even using GRMs to modify rewards from different environments. While these methods encounter efficiency challenges, they show promise in enhancing rewards on a larger scale, aiming for a more versatile reward system. We also highlight the importance of inference time scaling for LLMs, which runs parallel to scaling during training. Research has concentrated on sampling and reward model guided aggregation. Recently, long horizon chain of thoughts inspired by LLMs have shown encouraging results in boosting the model's reasoning abilities, representing another approach to inference time scaling. Additionally, studies have explored scalable rewards or verifiers to enhance the performance of policy models in areas like coding and reasoning. Therefore, our work on developing inference-time scalable generalist reward models may also contribute to improving the overall performance of policy models through co-scaling during inference.